Hello everybody, welcome back to iBuddy Science, and today we're going to be doing electrical energy and percent efficiency. Now, the first thing I want to do is start off with a Kickstarter. What do all three of these things have in common? Now, I want you guys to think about this first, but okay, so if you guys said that they're all sources of electrical energy, you would be correct. Now, I'm going to define a couple of key terms before we go on to more complicated stuff. Now, some key terms is that electricity is the movement of electrons between atoms, while electrical energy is energy generated by the movement of electrons from one point to another. Now, a very big misconception is that these two are the same thing, but they have key differentiations like energy compared to electricity, which is the movement. So in other words, electricity is the energy from electrical energy, or the other way around. Electrical energy is energy from electricity. Now, make sure you don't mix these up. This one is found in a lot of things, in a lot of applications, in turbines, for example. Electricity is just how it moves. So how exactly does a wind turbine generate electricity, as I just said? Now, a wind turbine, the first thing that happens is that wind, it essentially causes the turbine to spin. And after that, the turbine is connected to a rod, which is right here, in the generator. The magnet inside this generator then spins, and the magnet causes the electrons in the surrounding copper to move. And this causes current and electricity. This is not electrical energy yet. Electrical energy is actual energy that's being made. The movement of it is electricity. Now, after this, electricity is transported through homes. And this could be through a lot of things, such as step-up transformers and a lot of these types of units, which essentially convert it into ways that our homes can use. So here's another cleaner diagram of it, in case you guys want to take notes. So now we have a couple of applications, as I mentioned earlier: moving water, wind, steam. So here is an example of a nuclear reactor. It uses control rods, and it basically uses steam to cause the turbine to spin and go into a generator, which is then done through step-up transformers into homes. There's also a lot of other processes, such as using condensers to get the water into the control rods, heating up into steam. And this is an example of how nuclear energy works. Now, here's another example. This is hydroelectric electricity. This just uses the movement of water to harvest it into a turbine, which then turns into a generator, generating electricity, step-up transformer, and it's then transported to homes. So it's pretty similar to our wind turbine example here. They use these same things that get almost all of the energy that we get today, electrical energy. So now I'm going to do a key differentiation. What is renewable versus non-renewable energy? Now, renewable energy is energy that's be able to be faster or equal to the rate at which it's used. So an example of this is solar energy, because solar rays and solar energy can be replenished faster because we have so much of it and it's abundant compared to the amount that we're using. Now, there's non-renewable energy sources which can't be replaced as quickly as it's used. So, for an example, a non-renewable energy source is fossil fuels, since they form after millions of years, and we cannot actually be replacing them as quickly as we're rapidly using them. And at a certain point, we might not be able to have any fossil fuels at all. So they are non-renewable. So let's talk about a little bit more of a different concept. How exactly does electricity get to our homes? So here's a quick little diagram. I'm going to be giving you guys notes after this. But electrical current, first, in the power plant here, is generated at 20,000 volts or less and transported to 12 kilovolts. From here, it reaches a step-up transformer, and the step-up transformer has these thick wires that basically carry the current, and it increases the voltage. Now from here, we have these transmission lines, and these measure in 4,000 kilovolts, as you see, and these basically just carry the electrons from the step-up transformer, and this one is specifically used by malls or factories. Then we have a substation, which is a step-down transformer. This takes the energy and decreases the voltage. And by the way, the decrease of the voltage is now being able to use by malls and factories, not the high voltage transmission lines. Now, from here, the step-down transformer, it's 12 kilovolts. It goes to the step-down transformers, which then goes to 240 volts to our homes. And this is basically the distribution lines, which decrease the voltage so it's safe for homes. So what this guy does, this step-down transformer does, is that it makes it safe for malls and factories, while the step-down transformer like this one actually allows it so it's safe for homes. And here are some more notes about them, in case you guys want to see. Alright, now let's talk about what's happening in your home. Now in your home, there's basically a meter and a distribution panel. And in the meter, these guys basically track the electrical energy that's being used in your home. So here's the energy. And we also have the distribution panel here, which allows you to basically turn on and off different electrical outputs. So for an example, 50 amperes here, 20 amperes here, and it basically allows you to use all your utilities and all your electrical components in your home. So first, let's talk about meters. As I just mentioned, it tracks the amount of electrical energy used. And basically, utility companies can use this information to charge you and calculate your share of distribution, maintenance, and repair costs. So if you go outside your home, you'll likely see one of these things. Me personally, I did not know what it meant until now. But it's very interesting because you can actually see how it's measured in kilos. And it's pretty interesting because you can basically see your costs beforehand. Now here is a distribution panel. Now, as I mentioned earlier, it distributes electricity throughout your home, and this contains circuit breakers and fuses. Now, what is a fuse, first of all? Fuse is actually an interesting topic, because a fuse, this one's interesting because if there's a lot of current that's going through it or a lot of voltage, the fuse will melt, which prevents it from going through. So that's what this is basically. But the distribution panel or the circuit breaker is basically just a more a safer and more effective way of stopping the current to go through if there's a dangerous amount. So here are some applications of these, such as how it's getting transported. So what are 5 things in this room that use electricity? I want you guys to look at your room and think of 5 things that use electricity. So go ahead and do that. Alright, now we're going to go on the topic of how much electrical energy is used. Now, electrical energy is measured in kilowatt hours. What is a kilowatt hour? As you see here, we have kilowatt hour, and we have the amount of kilowatt hours per year. So, kilowatt hours. And basically, the way we think of this is that kilo stands for 1,000. Watt stands for, a watt hour basically stands for the amount of watts in an hour. And it's basically just a measure of energy. Yeah. So if we think about it like this, kilometer here, that's just a measure of distance, 1,000 meters, compared to 1,000 watt hours. So that's the energy source. So, yeah. So, how's electricity measured? In this way, measurement of electrical energy is a usage of 1,000 watts per hour. So, here's the next one. This is the measurement of energy. You guys might have heard it before. It's called the joule. And this is pretty important later. So, let's first talk about phones. Now, phones use about 2 to 6 watts an hour while charging. And in 2015, Ontario used 160 trillion watts per hour charging your phone for over 40 trillion years. Now, let me go to how we can reduce this electricity usage, because this is not very good for the environment. Now, first of all, is using renewable resources. For example, instead of using coal, we could be going to stuff like water or solar, wind, and electricity. Here, in 2005, we can see that this usage was a lot less. But now, we can see that there's a lot more of these usages, so it's better for us. Now, they should also recommend us to use electricity efficient tech. LEDs, for example, are very efficient, they last long, and they render colors very well. CFLs are light sources that aren't pretty efficient, but in the mid-size, and they're not too expensive, so you see these a lot. Incandescent are not efficient, not really long, and they render color really well though. And candlelights, they also render color well, but they don't have much of a lifespan, as you guys possibly know, because the fire pretty much melts all the wax, and they're not very efficient. So, what is efficiency? I've been throwing this word around, and you guys know what this is. Efficiency, basically it compares the total energy that comes out of a device with the useful energy that comes out. There's a formula for this. So here, as we saw earlier, efficiency is like this, efficiency like that. There's 2 lights compared to 3 lights. So we can safely assume that 5% of the energy creates light compares to 20% of the energy creates light out of the ratio. Alright, so what was that formula I was talking about? Well, it's the E out, energy out, over E in, energy in, times 100%. And this gets you your percent efficiency. So let's go ahead and try some practice problems. So here we're going to be using the grasp method. Basically, it's the given, required, analysis and solution, and paraphrase. So let's go on to it. We're given, let's first read out the question. There's 800 joules of energy entering a light bulb, which produces 40 joules of light energy. What is the percent efficiency? Now it's given that the total energy in is 800 joules. The output is 40 joules. And we need to find the percent efficiency. So in this case, we now need to do our analysis and approach. So I'm just going to write A and S here for a shorter format. But basically, we can just do this. So, we know that 40 is the output, as you saw here in the formula. And E input, because it says E input is here. So 40 over 800 times 100%. Now let's first solve this. If we do 40 over 800 on our calculators, we get 0.05 times 100%, which gets us 5% efficiency. Now, to paraphrase this, that's our final thing. We need to really do like a conclusion statement, which you can just do therefore with 3 dots. The percent efficiency is 5%. So here is a more cleaner solution for you guys. In case you guys want to see, that's our grasp. So they did the same thing. They required it. They give it. And then they do their solution and they paraphrase it. They didn't use the therefore statement, but as long as you have the word paraphrase, the teacher will get the main idea and the communication. So let's talk about the EnerGuide label. Now the EnerGuide label is basically just how much energy it consumes, and it depends. If it uses least energy, it'll be on the lower side of the scale, while if it uses the most energy, it'll use the highest one. As you hear, it gives you where the model is in the scale per year. So as you hear, our model here, the EnerGuide says that it's pretty much on the lower side, but still consuming a significant amount of energy. So, and there's also a type, and there's also something interesting here that says removal of this label before first retail purpose is an offense. So here's the logo, EnerGuide. It's basically just the Energy Star. So, yeah. So now we need to figure out what the cost of electricity is. So we have something called, on Ontario, basically they're called time of use price periods. So here we have all of the major times when the time of use price periods change. So we have midnight in the summer weekdays, midnight in the winter weekdays, and weekends and holidays with the midnight on the top section here. And that is these little top sections here. And then we have the noon. And we have the precise dates of them on the bottom. Now here we get different colors. Yellow means mid-peak, so middle cost. Red means on-peak, so a lot of cost. And green means off-peak, so there is little cost. So let's go over it. Let's say use your oven for 5 hours and use 0.8 kilowatts each hour. How much electrical energy was used? So let's just go and understand this. So we're given what? We're given that there's 0.8 kilowatts. We're also given that there's 4 hours. And what we need, which is required, is the amount of kilowatt hours. So the analysis and solution here, we're going to be using a little formula called energy is equal to kilowatt per hour. So that'll be times hour. So yeah, that's basically what we're given here. So energy is pretty simple now, because we're given how much kilowatts and how much hours. Since we know that energy is kilowatt hours, we can do energy equals 0.8 times 4, which is equal to 4 kWh, or kilowatt hours. And with a paraphrase, we can do 4 kilowatt hours of electrical energy is used. Okay, next one. Alright, so here is a cleaner solution of it in case you guys wanted to see it. So now we're going to be using those graphs as I mentioned earlier. So let's say the cost of electricity is 0.10 kilowatt hours and off-peak. The mid-peak is 0.15 kilowatt hours and on-peak is 0.20 kilowatt hours in price. what is the cost of using your oven between 5 p.m. and 10 p.m. In the summer. So we have our summer chart right here, 5 p.m. to 10 p.m. or 5 p.m. to 7 p.m. This would be our mid-peak, indicated by the yellow, so that's 2 hours there. And then we have our off-peak, which is 7 to 10. So we basically divide it into two sectors. So here, that would be 3 hours. Now we do our basic formulas. So we know that energy equals kilowatts times hours. So let's do off-peak first. The off-peak is going to be 3, because there's 3 hours. And the kilowatts of that is going to be 0.10. So it's going to be... Wait, hold on. Wait, 0.8. Yeah, so you would essentially do that. So since off-peak is 0.10, this would be energy equals 0.10 multiplied by the amount of hours, which would be 3. And if you don't know, 0.1 times 3 is 0.3. Now another one is energy equals 2 times, and we have a mid-peak, so let's do 0.15, and this would get us 2 times 0.15 will get us 0.3 again. And from here, the total energy used is 0.6 kilowatt-hours. Now, in this case, I actually didn't see something. The oven uses 0.8 kilowatt-hour per each hour. So you would actually just, I would actually assume that you don't actually use these rates. I think this was just misleading, to be honest, so. Or no. Yeah. Yeah, I think actually you would have to take these, you would first take this, take the rate of which it is. So for example, 2 times 0.8, because there's 2 hours here. So essentially with that approach, you would have to do something a little bit different. That's the main approach that I would saw here, but this part I did not see. So essentially what you would do is you would do 2 times 0.8 first, because there is 0.8. It oven uses 0.8 kilowatt-hours, and we do 3 times 0.8, and that will get us 2.4 kilowatt-hours, and this will get us 1.6 kilowatt-hours. Now from there you can just plug those in, and as you see here, you can pretty much just multiply those by the rates, and you add them up to get 0.48. So that problem kind of tripped me because I didn't see this recall part. We have to be a little bit sure about that. So that's pretty much the end of the lesson. I want you guys to practice. There's a lot of stuff posted. So